Last time we talked about how magnetic fields work, what they look like, what their shape is, and their direction. This time we're going to talk a little bit more about magnetism itself. So I have a rare earth magnet here. Now it's called a rare earth magnet not because it's terribly rare. There are magnets all over the place, but because it's made of minerals that are naturally magnetic. Nobody manufactured this and then magnetized it. It's just made of minerals that are magnetic. Okay, so this magnet attracts other magnets or repels other magnets. Oh, I don't want it to fall. There you go. They attract each other or they repel each other. Can't put them together. You got to trust me on this. I'm not a very good actor. Okay, so that's a naturally magnetic material, but I also have some other things that we know stick to magnets, but are not magnetic themselves. So here's my magnet. I also have a nail. Put it over here so you can see it. And they're attracted to one another. Okay, this nail is not magnetic in itself. If I have another nail, which I do, if I have another nail, they don't stick together at all, okay, because they're not naturally magnetic. So what these objects are that are not magnetic on their own, but are affected by magnetic fields, they're called ferromagnets, okay? Ferro means iron, so it's usually iron-based things, though cobalt and nickel are also magnetic, okay? And we're going to talk about why things are ferromagnetic. I have these two blocks here. They're metal. They are not magnetic in themselves, but when I put a magnet against them, it sticks to it. Okay, now this thing has become magnetic as well. So if all goes well, I should also be able to stick a nail to it. Okay, now this nail is not here because this is magnetic. It is sticking to this thing because now this is magnetic. This magnet has caused a magnetic field to be created in this piece of steel. Okay, but the moment that I remove that magnet from the top, it's no longer magnetic itself. So this object would be called soft ferromagnetic. Okay, so there's two classes of ferromagnets, soft and hard. Soft ferromagnets, it's not that they're actually squishy or anything, it's that it's easy to magnetize them, but they demagnetize really easily as well. So maybe you've tried this before in your elementary school days, but when I was a kid, we used to take our scissors, and then when we had magnets in class, we would like rub our scissors with magnets, and then when you'd take the magnet away, the scissors would be able to pick up paper clips and stuff like that. The scissors would remain magnetic even though they weren't touching a magnet anymore. The scissors would be called hard ferromagnetic. So a soft ferromagnetic material is easily magnetized, but also easily demagnetizes. It doesn't stay magnetic for very long. A hard ferromagnetic material remains magnetic long after the magnetism has passed. So natural magnets exert forces on each other because they produce magnetic fields. And so the magnetic fields interact with one another, and then you get repelling or attracting depending on which side you're talking about, which pole you're talking about. But why do magnets attract nails? Nails aren't magnets and they don't create a magnetic field. So what exactly is happening there? So we can explain ferromagnetism using something called domain theory. So I want you to look at the top left diagram over here. This is we're going to say a microscopic view of a magnet. Okay, so we're looking at a bar magnet, we're looking at its inside. You wouldn't actually see this if you cut a magnet and then looked inside, but this gives you an idea of what's going on. So all of these little arrows here, all of these little sections, they are domains. So a ferromagnetic object like a nail is filled with all of these individual magnetic sections. Okay, and that happens because of electron placement and spin, that type of thing. That's more complicated than what we're going to get into. But notice how all of these magnetic sections called domains are all just randomly oriented. So we're assuming that this arrow is pointing north. It's pointing to the North Pole. So when all of these domains are randomly oriented, this magnet doesn't create a total magnetic field. Okay, you can think of it like this. All of these little magnets are creating their own little magnetic fields like this. Like this. Okay, so that's that one. But then this one is pointing a little bit differently. Like that. And this one is just totally different. Like this. And so when you add up all of those individual little magnetic fields, they just cancel each other out. Okay? And so a ferromagnetic object that has not been magnetized has all of these randomly oriented domains that add up to a zero net field. Okay? But when you take one of those ferromagnetic objects and place it inside a stronger field, or inside any field, like this diagram on the top right, you'll see how these arrows, they all start pointing the same way. Okay, and when that happens, you get a total magnetic field in this direction. Okay, and so now this object, now that it has all of its individual domains lined up, it's going to start creating a net field, something like this. Okay, same thing on the other side, and its direction is going to be the same direction as the domains are pointing, like this. Okay, so now that all the domains have lined up, you basically have another magnet. And that's why when we looked at that little iron bar over here, this thing, when it was attached to the magnet, then suddenly it could also pick up nails. Okay, so when we did this, now this steel bar here, it's also magnetic. And so it can pick up nails as well. Okay, it's not very strong and makes me a little bit nervous that it's going to fall off, but ferromagnetism is what's happening here. The domains in this steel bar have lined up, so they're making their own magnetic field now, which makes this thing stick to this magnet and also allows it to pick up this nail. Okay, all of the domains in here are all lined up. Let's see if we can stick one more nail onto the bottom of this nail. I doubt it, so we'll see. Careful now. I can feel it trying, but it's not going to work. It'll be close. I can feel the magnetic force on the bottom though. Oh, if only you were here with me, you could feel it and you would be so amazed. Okay, so that's domain theory. Every ferromagnetic object is made up of little magnetic areas called domains, and when you can get them all to line up due to an external field, then you can make them magnetic and make their own magnetic field. Okay, same thing happens over here. If we put this ferromagnet into the magnetic field over here, it's going to line up with the direction of the magnetic field it's in and start creating its own magnetic field like this. Okay, same thing on both sides. Now, if you were to break a magnet in half, I don't really want to do that, but if you did, so I take this magnet and I break it in half. Now do I have a north pole in one hand and a south pole in the other hand? No, that's not how it works. So because of domain theory, if we look at this magnet over here, let's call this just a regular magnet. If we split it in half down this line, notice that on this side, all of the domains are pointing to the right, and on this side, all the domains are pointing to the right. Okay, and so that would make this the north pole of this magnet, and this would be the south pole of this magnet. Okay? And then when we're looking at this magnet that we've now ripped off of the original, we have the same thing going on. This is the south pole, and this is the north pole. Okay? The domains don't allow you to split off a north pole in one hand and a south pole in the other hand, because inside each section you're going to have a more southern end and a more northern end. That's not really the right word, but that's all I know how to say. Okay, and so then what happens when you break a magnet apart is this. If you take a bar magnet and you break it apart, you end up with a north pole and a south pole in one of your sections, and a north pole and a south pole in your other section. So this idea of ferromagnetism can also be applied to the Earth. The Earth's core, its inner core, is made of solid iron, but then there's this layer of liquid iron around that inner core, just like this. So here's the Earth's inner core, solid iron. Here's the Earth's outer core. So although the Earth's inner core is solid, it's extremely hot. Okay? And because it's so hot in the center of the Earth, the outer core, which is liquid iron, starts to produce these convection currents. That's just because the liquid iron heats up so close to the center of the Earth, and when it heats up, it pushes it outward, and as it cools, it drops back down, heats up again, and then it gets pushed outwards again. Okay? And so you get these convection currents going on, and when you have moving liquid metal, it also produces electric currents. We'll talk about this a little bit later on, but moving currents like that, an electric current, causes magnetism. It causes a magnetic field to form. And so then down here, what you see is the Earth with a picture of its magnetic field as well. So the Earth produces its own magnetic field, which is why a compass will point you to where north is, because a compass is a little bar magnet and it will line up with the Earth's magnetic field. But something odd happens with using a compass in the Earth's magnetic field. We know that a compass, the red part, is the north pole of that magnet, and so it is attracted to south poles, right? Opposites attract. The white part of the bar magnet is the south pole of that magnet. It's attracted to north poles. So when I use this magnet, you're not going to be able to see this very well, but it points at that direction. That direction is north for me. Why is the north pole of this magnet attracted to the north pole of the Earth? Shouldn't they be repelling each other? It actually turns out that what we call geographic north is the magnetic south pole of the Earth. Okay? So a compass will point you toward geographic north because geographic north is actually magnetic south. Okay? And so here's what's happening. This is kind of a representation of what's going on with the Earth. You can think of it as a large bar magnet. The south pole of the Earth, the magnetic south pole, is at the top of the Earth, is at the geographic north pole. And the north pole, magnetic north, is at geographic south. So then the magnetic field would be drawn like this. These are the magnetic field lines of the Earth. And so then when you put a compass here, it's going to go like this. North pole is going to point that way. South pole of the compass is going to point that way. It's going to line up with the magnetic field lines in the appropriate direction. Okay? And so the north pole of your compass will point you toward geographic north because it's actually magnetic south. But the magnetic south pole doesn't have to be exactly on the geographic north pole. Okay? And actually what has been happening is that the magnetic south pole has been moving. If you look at this diagram over here, you can see that in 1900, the magnetic south pole was right over here. Okay, that's in the Canadian archipelago, or archipelago, however you want to say that word. And in 1910, it moved a little bit farther this way, and it's been kind of traveling this way all along. 2005 is the last measurement on this diagram, way up here in the Arctic Circle. Okay, and so imagine trying to navigate to the North Pole using a compass, let's say before there was GPS. It could have been very confusing. Your compass would have told you to somehow end up in the middle of the Canadian archipelago when you were trying to find geographic north. Okay, and it wouldn't have worked very well. The question is also begged, what happens if the North Pole or the magnetic South Pole flips over the top of the Earth and then just keeps going the other way? Is it someday going to switch directions? Possibly. We don't know. And that brings us to our final idea. There's a difference between magnetic south and geographic north. Okay, and so your compass is going to point you in a different direction than maybe you're trying to go if you're trying to get directly to geographic north. Even if you're just trying to navigate using a compass somewhere in the northern hemisphere, knowing the difference between magnetic south and geographic north, that's important. And so we have this map here. This is a map of magnetic declination. Okay, magnetic declination just means the difference between true north, geographic north, and magnetic south. Okay, this black line that you see right over here, that black line is the zero line. So if you were standing somewhere on this black line, your compass would point you directly to geographic north. If you are not standing on that line, though, your compass won't quite point you in the right direction. It'll miss a little bit because of the difference between magnetic south and geographic north. So where we are, over here, southern Manitoba, we have a magnetic declination of about 3 degrees. Okay, that means that there's a 3-degree difference between what your compass tells you and where the true north actually is. Okay, and if you would move farther north, it would become much different. If you're over in BC, it's a much bigger difference. Okay, and so you need to know, if you're using a compass to navigate, you need to know the difference between the true north and where you're standing, because your compass is not probably going to tell you quite the truth. So if you're looking at your compass like this, if you are east of true north, if your compass is pointing east of where it should be, your declination is positive. And if it's the other way around, if your compass is pointing west of true north, that would give you negative declination. Okay, so when you're looking it up, you'll find that either your location has positive or negative a certain number of degrees of declination. And there's one more thing that we're going to look at, and that's called inclination. Okay, now you have to realize that magnetic fields are 3-dimensional. It's not on a piece of paper. We're looking at a bunch of drawings and diagrams here. They're all 2-dimensional. But in reality, magnetic fields are 3-dimensional. Okay, and so if you had somehow a 3-dimensional compass, it wouldn't be laying flat like this. It would be pointing upward somewhere, because the Earth's magnetic field may be where you are, pointing inward toward the Earth. Okay, so if you look at this diagram on the right over here, this is the Earth. The magnetic field lines of the Earth, let's say right at the magnetic South Pole, are pointing straight down into the Earth. Now, if you had a regular compass, your compass couldn't tell you straight down. It would just spin in circles. But if you had a 3-dimensional compass somehow, it would point you straight down into the Earth, because the magnet in the compass will line up with the magnetic field lines. So let me give you an example with our Earth magnet and the compass. Okay, so at the equator, right over here, the magnetic field is pointing straight this way. And then as we move the compass toward the Earth's geographic North Pole, magnetic South Pole, then the compass needle starts to point straight down. Okay, so if you were standing at the magnetic South Pole, the Earth's magnetic field would be going straight down through you. But if you're standing at the equator, the Earth's magnetic field would be passing along the ground right by you.